So watching one of the first day videos last night. It's really cool to see.
Okay, before we start, we have 2 more minutes. I'd like to do an experiment. We already had 2 measurements, which were inconclusive. Can you hear me? So we already had 2 measurements. I'd like to make a third one. How many of you studied the C=1 compact boson in school? What's the opposite question? Who never heard of the C=1 compact boson?
Never heard of is different from didn't study.
Who heard about it but never studied it? What was the question?
Who studied it and didn't know that's what it was called?
Ah.
Can I make a quick announcement, Nadi?
You're the boss.
All right. So, but before Nadi starts, I just wanted to, now that we've been here a couple days, starting to settle in, to put 2 things in your minds to think about that traditionally have happened at TASI. One of them, Ken mentioned it a little bit on the first day, but students have traditionally done sort of student talks to each other. The faculty do not come to these talks. Over the years, we have reduced the length of these to 5 minutes. The idea is to really just say, hi, I'm so-and-so, I'm from this place, I study this, let me tell you a couple things about it. It has the advantage of you can figure out an elevator pitch of what your research is, and it also means you don't stress out about giving some 30-minute talk to everybody and then, miss the lectures because you're trying to prepare the talk. The idea is just to explain what you're doing to each other, and they're traditionally done in the evenings, and we do not organize them, you organize them. So what I was hoping for is if 1 or 2 people would be interested in sort of volunteering to coordinate these. Is anyone interested in coordinating student talks? Well, let me see if anyone's instantly interested. There's 1 up back there. Okay. 2? Okay. So why don't you go talk to Ethan? This is Ethan Neal, everybody, the co-director, if you didn't meet him already. He can give you access to the wiki, and you can sort of start to put those things together. So and thank you for volunteering. The other thing I wanted to bring to your attention was, as you have noticed, it is a fine TASI tradition to have these T-shirts. So the T-shirts are always designed by the student class, and traditionally, sort of a box is ordered. We'll get a few for ourselves, which we will pay for, but then you pay for your own. Is anyone interested in sort of leading up the T-shirt design and acquisition project? Is there a hand? Yeah? Great. So why don't you come talk to me and Ethan afterwards, just so we know who's doing it and who to communicate with. So thank you all for volunteering to do that. And like I said, these are mostly things that you all will do amongst each other in the dorms on the Discord without so much our input. Okay, well, without further ado, let me turn it over to Nadi, and I'll give him his extra 2.5 minutes on the other.
Okay, thank you. Thank you. So in the first 2 lectures, I talked mostly about quantum mechanics and a little bit about 1 + 1 dimensional field theory, about the C=1 system, mostly in order kind of to set the notation. And it turns out that Yifan will talk a lot more about the C equals 1 system in the continuum. And instead, what I'll present here is a completely self-contained story of the C equals 1 system on the lattice. So even if you never heard of the C equals 1 system, you are OK. So let me just review some things that we'll be aiming toward. I had a picture on, this was a one-parameter family of models. I will soon derive it, but I just want to remind you what I was saying. It's a one-parameter family of scale invariant theories labeled by a parameter R. And at R equals 2, something special happens. Sorry about that. So the model has G of C equals 1 is U1, which is called momentum, for reasons that are irrelevant for what we're doing here, U1 winding. And for the condensed matter people in the audience, sorry, this is charge and this is vorticity. And if we take that as the IR symmetry, we can have different symmetries in the UV, and we discussed different examples that we could have. In the simplest case, GUV is only U1, U1, semi-direct Z2. And then the model is gapless here and gapped here. And when the model is gapless, we get this GIR. When the model is gapped, there's no symmetry at long distances. And as I was corrected, it's called the G is 1, just the trivial group. So keep that in mind. I'm going to derive that several different ways. And Yifan will say a lot more about that. OK, now let's put that aside. And for the rest of these talks, I will not be in the continuum. I'll be on the lattice. And there are several reasons we would like to do that. Partly, the spirit of these talks is to understand symmetries. And we talked about symmetries in the UV and in the IR and emergent symmetries and so forth. But more importantly, I want to talk about anomalies. We've already discussed anomalies a little bit, especially in quantum mechanics. And I postponed anomalies in field theory, which are more subtle. There were some questions from this part of the audience, because I'm going to do them now from a different perspective. So the story of anomalies has a very long and convoluted history. Convoluted because it has tons and tons of misconceptions. So it's kind of in the spirit of once talks. People thought A, and then A was wrong, and then they thought B, and then B was wrong. And eventually, we converged on something. And when I went to school, anomalies had already been known. And they were associated with the fact that there's an infinite number of degrees of freedom. And the system has infinities. And the infinities need to be regularized. And there are subtleties in how you regularize the infinities. And because of these subtleties, there are anomalies. So I've already gotten rid of this thing because I had an example with the two-level system that has anomalies. You don't need an infinite number of degrees of freedom. Then a new generation of physicists, it's like quantum mechanics. Every new generation has to have his or her new misconceptions. So the new misconceptions are that a system with anomalies is inconsistent. It's consistent only if it's on the boundary of some higher dimensional theory, and there's a whole story going around that. I think the two-level system also gets rid of this misconception. Nobody's going to argue that the two-level system is inconsistent. It needs to be at the end of some bulk theory. But there are a lot of things in condensed matter physics which look a lot like they're related to anomalies. And somebody like me says, I couldn't even figure out an anomaly in what? Because an anomaly means that there's a symmetry, and there's something funny about the symmetry, and therefore you extract some consequences from it. And the usual way of thinking about anomalies in terms of coupling to background fields and so forth does not work that easily when you go to these systems. For one thing, we don't have Lorentz invariance. We don't even have translation invariance. We have only lattice translation. So the whole idea of this notion of continuity and smoothness that are important when we classify various topological objects does not exist when space is a lattice. So when we discuss winding number or other instanton number, these things don't exist on the lattice because every topological thing can shrink and shrink and shrink and fall between the points of the lattice. Now, there are all sorts of other things related to that that are very puzzling. There's an issue whether the symmetry acts on site or not. This is a phrase from the condensed matter literature and also was brought up by a question here. We'll discuss that in detail. And there are also there are also anomalies in the literature associated with lattice translation, which is very interesting because in the continuum, it's known that there is no anomaly involving translation. It's a fact about life. There is no anomaly involving translation. All the anomalies, especially in simple systems, involve internal symmetries, not translation. Whereas the condensed matter people love anomalies associated with lattice translation. So how can that be consistent? There's a whole thing about emergent symmetries. I talked a little bit about it earlier, and people asked, there can be new symmetries, and they might have anomalies, but these anomalies cannot be matched with anything in the UV because the emergent symmetry is only in the IR. So how can you possibly match it with anything in the UV? And the list goes on and on. So I'm going to answer all these questions. That's my goal. And instead of giving a general theory, I'll focus on an example. And the example I've talked comes under the name of XY model. So there are actually two different things that come under the name of the XY model. Two different things. This is one of them. This is kind of the canonical example of a field theory that people are interested in. It's the simplest one. It's a system in 1 + 1 dimensions. It's usually studied in the context of classical statistical mechanics, namely Euclidean space-time, perhaps with a lattice, with some action. But I'm going to do it in a Hamiltonian formalism. From this moment on, almost everything I'll do till the end of my lectures, including the next one, I'll be in a Hamiltonian formulation on a spatial lattice. So I'm just limiting myself to that. We can easily extend that to the Euclidean version. So model number one, I'm going to write a Hamiltonian, which is the Hamiltonian version of that. I have a lattice with sites labeled by J. I'm going to use periodic boundary conditions. And there's a Hamiltonian. On every site, there's a coefficient here, pi j square minus j cosine phi j plus 1 minus phi j. And phi j is identified with phi j plus 2 pi. And phi j prime is I delta j prime. So what do we have here? We have a sequence of rotors. At every site, we have a particle on a ring, this phi, very much like in our quantum mechanical example from yesterday. So on every site, we have a rotor. And this is the momentum conjugate to the coordinate. And there is coupling between nearest neighbors. And since phi is circle valued, we can write a cosine, but just write 1 minus phi 2 square. And I use periodic boundary conditions, so when I'm coming to j equals L, this is L plus 1, which is really the same as 1. So this is the model. And this model depends on two parameters, U and J. One of them is an overall scale. So what the model does depends only on the ratio between them. And there are trillions of papers analyzing this model. Right? This model was beaten to death in all sorts of ways. And one way to think about it is that imagine the coupling is very strong. J is very large. So these phis want to be near each other to minimize the energy. So these phis want to be near each other. So the phis are very near each other, and they are almost smooth. So you can identify that, you can approximate that by the derivative in space of phi with respect to x. And that goes over to the Hamiltonian of the C equals 1 model. And indeed, this model, when J is big enough, flows to the model up there. And if you just match the coefficients, then r to the fourth, that r was defined there, is 2 pi square j over u. So I said, let's assume that j, first of all, the spectrum depends only on the ratio. So and I looked at j large with u of order 1. So it depends only on j and u. And then you can expand, assume the coefficient here is large, approximate this by a continuum, and match the coefficient with the Lagrangian I wrote before, and you get this answer. But then this is only approximately true, order u over j. So we are going to get the model for large R. And then you make the radius. Then you change the parameters. You change j over u. It makes R smaller. So you move to the left. And the phase transition happens at R equals 2. And that corresponds to j over u approximately equals to 0.8. And that comes from numerical calculations. So it fits the picture we had there. There's a formula for R in terms of j over u. When R is large enough, or when j over u is large enough, this model flows to that one. But then when R becomes smaller, we have a transition and the model becomes gapped. Why does it happen? That's easy to understand. And in fact, I already gave the answer yesterday. This model has only a U1 symmetry. This model has only a U1 symmetry. This is JUV, and the U1 maps phi at every point plus alpha, and alpha is circle valued, and the Z2 maps phi to minus phi. Notice the similarity to the various examples that I had yesterday and the day before. So that's the symmetry of the model. The winding symmetry is an emergent symmetry. But I gave you a formula for the dimension of the lowest dimension operator that violates the winding symmetry. And that operator at large R has very high dimensions, so it's very irrelevant. So it doesn't matter whether it's there or not. The low energy observer thinks it's not there, and we have the gapless theory. As we make J smaller, R becomes smaller, we move to the left, and at some point this operator becomes relevant. And once it's relevant, it cannot be ignored, and it triggers the transition. That's the BKT transition at R equals 2. So this is model number 1. Now, high-energy physicists love the C equals 1 model because it's being used all over the place in string theory or whatever context you learned about it. It's also the simplest the simplest field theory to study. It's exactly solvable. It has lots of lessons. And Ifan is going to have a lot of fun with it. I'm sure you will also have a lot of fun when Ifan is having fun with it. Showing that it has all sorts of marvelous things, non-invertible symmetries, etc. So it's a good laboratory for a lot of things. However, that ain't it. This one has the transition. And so it's not the same model. And the model we are interested in has all sorts of features like T-duality and so forth that you might or might not heard about, but this one doesn't have it. So I'd like to present a lattice model that has that symmetry. So before I do that, I'd like to share a misconception. I found Juan's talks very inspiring, kind of explaining the misconceptions. So when I went to school, this thing was already fully understood. And the logic was, there's no way to get the winding symmetry on the lattice. There's no way to get the winding symmetry because, as I'm going to show you, there is an anomaly involving the winding symmetry and the momentum symmetry. Now, you cannot possibly have anomalies on the lattice because anomalies are associated with divergences and so forth. So there's no way to get the winding symmetry on the lattice. Therefore, there is no way to exclude the winding operator. And therefore, there is no way to penetrate the gapped phase. So you can try all day, you are not going to find a lattice model with a winding symmetry. that will allow. So what you need is a lattice model with a winding symmetry, so you can penetrate this barrier and be in the gapless phase. Now, this was a very common misconception. So I'm telling you now it's a misconception, but this was a very widely held point of view. So I'm going to do that. So model number 1, so I'm going to change the model. So I'm going to put subscript 0 because it's not going to be the same coefficient. So I have some u0 over 2 square, pj square, sum over j, minus j0 plus j0 over 2, phi, lowercase phi, j plus 1 minus phi j, 1 any square. So let's imagine that it's the same model, but we leave out the periodicity. And then if we don't have the periodicity, we don't need to write the cosine, and we can just approximate it by a parabola. So that's what we did. Example of a physical system where this happens, you have atoms in a line, and the atoms can vibrate, and there's Hooke's law that tells us how much energy it costs when they vibrate. So this is the distance between two atoms as they vibrate, and this is the momentum conjugate to phi, and that leads to phonons. This model is actually exactly solvable. You can diagonalize this Hamiltonian, you can take it as a problem, and it's also a textbook case. But that's not what we want. It's not what we want because it's very important for us that phi is periodic. In fact, if you ask yourself, what's the symmetry of this model? It's not 1. The global symmetry is R. Phi j goes to phi j plus, call it beta. But beta is not circle valued because phi is not circle valued. So we can just shift it by an arbitrary amount. So this model is not going to do the job because phi is not circle valued, problem number 1. Number 2, it also doesn't have the winding symmetry. This issue was addressed by a physicist called Villain, although it had appeared earlier by various authors. So what Villain said, he did it in a Lagrangian formulation, but it's essentially the same thing. So he said, let's introduce on every link of the lattice, introduce an integer, n j plus 1. So on the link j plus 1, and n j plus 1 is an integer. So this is another model. Now it looks like things are periodic because I can shift phi by 2 pi, only on one side. I can shift phi on one side by 2 pi, and shift the corresponding links by similarly by an integer. And I put the 2 pi here. Now, instead of saying that n is an integer, we can be a little bit more sophisticated and say, let's say that n, j plus 1, has a conjugate momentum, e j plus 1 prime, and that's I delta j plus j prime, j prime, and postulate that e j plus 1 is identified with e j plus 1 plus 2 pi. So E is circle valued. E is circle valued. And if E is the coordinate, then N is the momentum. More precisely, N is the momentum, and it's quantized. So instead of postulating that N is quantized, we could say that its conjugate variable, E, is circle valued. Is that clearer? So if I just take this Hamiltonian and I postulate that there is an E like this, then it basically quantizes N, and I can check that I can take each phi j and shift it to phi j plus an integer kj, and shift n j plus 1 and I need the 2 pi here. You can check that this is a symmetry of the model. Now, the rules of the game in field theory and on lattice models is that once we have a symmetry, we should write everything consistent with the symmetries. So I can introduce another coupling constant. And we need to put a cosine, because it's circle valued. I can put a minus sign to really make things easy. So this is my new model. So what's the cast of characters? We have phi and p, which are real variables. N can be thought of as real, but E is in S1. That's the cast of characters. In this model, known as the Villain model, Villain did it in a Euclidean formulation, but it's exactly the same as this one. This is the Hamiltonian version of it. This model is a close cousin of this one. Let's compare. First, they have the same symmetry. We said before that here we have only symmetry shifting by a real number. But now, if this number is an integer, I can absorb it in what I can call a gauge transformation. So therefore, beta is effectively compact. So we have a U1, which I'm going to call U1M symmetry. There is also a Z symmetry. I can flip the sign of all the variables, and the Hamiltonian is invariant. Very much like this one. So the symmetries seem to be the same. In fact, this Hamiltonian is another symmetry, a very big one. At every site j, I can act with e to the I, e j, j plus 1, minus e j minus 1 j. So these are the two links from the two sides of the site, minus 2 pi I pj. So let's check it. The term with e commutes with these two. So this guy commutes. This guy also commutes, because all these things commute with it. The only non-trivial term is the term in the middle. What this thing does is to shift phi j by an integer. And what this thing does is to shift the ends by appropriate integers. That is the same as the transformation that we did here. So the symmetries of this model is actually much larger than the symmetry of that. All the symmetry that is independent of J is exactly the same. These are global symmetries. But in addition, this model also has a separate symmetry acting at every site. Who knows what this is called? A separate symmetry that acts at every site. That has a name. That's a gauge redundancy or gauge symmetry. So that's a gauge symmetry. And the reason, and why did I use the character G? Gauss. Right, very good.
Why are you calling this a symmetry if it doesn't mean?
You're really preaching to the wrong person on this issue. Okay. It should not be called symmetry.
Okay.
Where is Ken? So what is this called? Imposing that? That has a name. Gauss law. Now, Gauss did not quite study this system, but it was actually not that different. Why did I denote E, this thing with an E? Anybody have any idea? That's the electric field. That's the electric field of the gauge field N. And what you see here in the exponent, if you think of these two E's as being, these sites being near each other, this is the derivative of the gauge field. This is divergence E, and this is rho. But since it's periodic, I exponentiated it. Let's discuss the symmetries a little better. So the system we are studying now is this Hamiltonian, and that's very explicit. When the number of sites is small, you can solve it by hand, put it on Mathematica, and really diagonalize the Hamiltonian. And when L is large, you can put it in the computer and just diagonalize the Hamiltonian. you take this Hamiltonian, you impose this condition on every site, because otherwise you're going to get a huge Hilbert space. So we impose on every site G equals 1. And that model is a very close relative to this one. In fact, they are almost, even numerically, they are almost the same. And again, there is a transition at some value of U0 and J0. Let's discuss the global symmetries a little better. We have a U1 symmetry that shifts phi goes to phi plus alpha. Which operator does it? What is the U1 charge? Notice how similar it is to the examples earlier in this lecture series. The operator that shifts phi is Pj, sum over j. Right, this operator, if I commute it with phi, I'm going to get the constant with alpha. If I exponentiate that q, I'll get the charge. But somebody could say, wait a minute. Phi started its life as a real variable, and p started its life as a real variable. So is this electric charge quantized or not? Do you understand the question? Not the answer, just the question. So phi, as we started, phi was real, and p was real, and n was real. And the only thing that was a little bit peculiar was E, which was circle valued. And we said that the global symmetry was R because we can shift phi by an arbitrary constant. And then we said that if the constant is 2 pi times an integer, it's the same as a gauge transformation and therefore should not be counted. But we would like to see it from here. Let me prove that. Let's look at this Gj and multiply it over the whole lattice. So on one hand, this is 1, because at every site, this has to be 1. On the other hand, I take these guys, and I multiply them one after the other. So the e's cancel in pairs. Right? It's kind of a telescope. They cancel. And what I end up with is e to the minus 2 pi I sum over pj. So what do we learn from that? We learn that the sum of the pj's, this thing, which is this guy, has to be an integer. So this is kind of a sanity check. This model has a U1 symmetry, and Q is quantized. Yes?
Doesn't it depend on what you choose GJ to be at each site?
I impose it to be 1 at every site.
But, I mean, would this change if you chose something else?
Oh, yeah. It will change, and we will do that in a lot of detail. So just to give you kind of a forward looking, that's what's called a defect. And it will be crucial in this talk, and it will be crucial in EFANC's talks. And I'm sure you'll hear a lot about defects in this school. Right? Where are the organizers? Yeah, you'll hear a lot about defects. Okay, so we worked very hard. We found another model, but it's not that different than that. It has the momentum symmetry. It has the Z2 symmetry. The spectrum is very much the same. And you get phase transition at R equals 2. But with this model, we can do something very interesting. Take this model as is. And for no good reason, set G equals 0. So I'm going to tune the parameter G to be 0. Just one parameter to be 0. There might be higher order terms like cosine 2e, but let's not discuss them for the moment. But I'm setting G to 0. Then something interesting happens. So let's first discuss no potential for E. Then this operator, and for convenience, I put a minus sign out front. Okay, I'm going to call QW. This operator commutes with the Hamiltonian. Let's check it. N doesn't know anything about P, they commute. It doesn't commute with this guy, but we have set this guy to 0. And we come here, N also commutes with every term here. So this charge is an integer, and it commutes with the Hamiltonian. It's an exact symmetry of the system. Now, one might argue that the local quantities, these guys, are not gauge invariant, or in terms of Gauss law, they do not commute with Gauss law. So I would like the charge density to be gauge invariant or to commute with Gauss law. So I'm going to write this term as 1 over 2 pi, sum over j, phi j plus 1 minus phi j minus 2 pi and j plus 1. So you can check that it's the same thing, because when I sum over j, these guys cancel each other. And we have a minus sign, which will end up being this minus sign. And the 2 pi here cancels the 2 pi here. Yes? Periodic boundary conditions. I said that from the beginning. We have periodic boundary conditions throughout these lectures. And I said it when we were here. I said when we get to the last term, j equals L. So here we have L plus 1, but that we identify as 1. This makes sure that we have periodic boundary conditions, so all these terms cancel. So what do we see here? We have a new conserved charge. We had the momentum conserved charge. Now we have a new conserved charge, which we interpret as winding charge. That's the U1 that we have in the infrared. So by tuning G to 0, we got a new U1 symmetry. And now we can address all the questions that were asked before. For example, do we have an anomaly? We know in the continuum there is an anomaly. Do we have a BKT transition? Okay, this is just another model. In fact, this model is exactly solvable. So we can diagonalize the Hamiltonian by hand and check it. Is it true that it kills the BKT transition? Is it true there is an anomaly? How do we diagnose the anomaly? And so forth. So all these questions can be just worked out very explicitly. And I did not do it in the continuum because we're going to do it directly on the lattice now. Historically, it was first done in the continuum. Questions? No questions. So both the momentum symmetry and the winding symmetry charge, this is Qm, and the winding symmetry charge can be written as a sum of local terms. So let me write that. Where QJW for winding is this combination, and the local quantity here is this. How do we usually refer to such a thing that we summed over to get the total charge? Charge density, yeah, that's called charge density. So Qm is the momentum charge density, and Qw is the winding charge density. So usually this is done in the continuum. It's very standard in the continuum, so we'll do it in the lattice. And when we have two operators, the first thing we do, we ask ourselves, do they commute? So let's commute them. These guys live on the links, and the momentum guys live on the sites, and let's commute them. So Q winding is this thing, and Q momentum is this one. So this has P. P commutes with N, and the commutator with phi is simple, just delta, right? So the commutator is I, because commutators always have I, over 2 pi. It came from this 2 pi. And then we have delta of j plus 1 j prime minus delta of j prime. What does it mean? It means that if this thing lives on the link, and this is on a site. If the link and the site do not touch each other, the two currents or the two charge densities commute. But when they touch each other, the commutator is non-zero, and we get 1 over 2 pi or minus 2 pi, depending on whether we touch this site or that site. Question?
Should the momentum density be at J prime, not J?
Yes, thank you. You do get extra credit for this. Here it doesn't matter. You want me to put a prime here?
No. So in commutator you have JJ plus 1. Q winding is JJ plus 1.
Yes, because the J, this thing with the 1 over 2 pi is Q winding J plus 1 with the 1 over 2 pi. I hope I got it right.
It was just bothering me that you didn't have the comma J plus 1 on the Q winding.
Ah, thank you. Thank you. You also get extra credit. Thank you. And thank you, Oliver. But you're not going to get the credit. Question. Who knows what this thing is called? This commutator. So this commutator, as far as I know, was only written recently, but it has a very old name. I think I heard the right answer. Yeah, this is what's called the Schwinger term. And first written down by Schwinger, long time ago. Schwinger wrote it in the continuum. In the continuum, this thing becomes delta prime of x minus x prime. And this is the lattice version of delta prime. So I decided not to tell you about anomalies as associated arising from Schwinger term in the continuum because I thought I would do it directly on the lattice. In fact, why did I call it an anomaly? Let's discuss that. Why is it an anomaly? We have two symmetries, QM and QW and QM. Let's take this expression and sum it over J prime. So we sum over all J prime. So that means the QW, some link, with QM. What do we get here? For a sum over J prime. Let's sum this expression over J prime. 0. And I can swap M and W. So not only do the charges commute, one charge commutes with the charge density of the other. So we have two charge densities. The charge densities do not commute, but the charge of one commutes with the charge density of the other. That was already true for Schwinger when he wrote this expression. This expression in the continuum has lots and lots of applications coming from the Schwinger model in physics, a central extension of Kac-Moody algebra in mathematics. It's connected to a lot of things in string theory, and you'll probably discuss some aspects of it. And now we see it on the lattice. And in fact, we can have the lattice very small. We can set L equals 1. So if L equals 1, it is 2 degenerate, and you don't see the full structure. But for L equals 2, you already see almost the whole structure. And so you can take a lattice as an exercise, a lattice with 2 sites. First one site is a warm-up, and then 2 sites. And if you're really adventurous, go to 3 or 4. And you can see all these anomalies are there. Yeah, you don't need an infinite number of degrees of freedom to have these anomalies. We'll do within a second, not a second, 5 seconds. We'll have other boundary conditions, and you will see that the story changes in a very interesting way. But for the moment, let's stick with this one just a little bit. This is related to another question that was asked earlier. Yeah, why I said Gauss law to be 1. You asked that, yeah. Superficially, it's not clear that the two have anything to do with each other. The buzzword that is associated with both is defects. And you will see that defects changing Gauss law, changing the boundary conditions, all these things are synonymous with each other. Also the same as the background gauge field. And I'm sure this will figure in Yifang's talks, but in the continuum. Now, when we have a symmetry, one of the first things we ask, what happens if the symmetry is not there? If we change the Hamiltonian and break the symmetry. So one thing we can do is turn on e to the I integer n times phi j, product over j. Which symmetry will this break? The momentum or the winding? The momentum. And why did I choose the integer, the coefficients here to be an integer?
Does it break down like Z or something?
The z symmetry, not zn. We want to make it gauge invariant, or in other words, we want it to commute with Gauss law. Conversely, I can add this guy. So for m equals 1, this is the same as this cosine. But we can also add that with m equals 2 and not add it with m equals 1. This breaks the winding symmetry, and depending on m, it breaks it to a discrete symmetry. And depending on m, the BKT transition, if m is 1, the BKT transition will be here. If m is 2, the BKT transition will be here at r equals 1. And if m is 3, the BKT transition will be at lower and lower values of r. There was a hint? Yes? These? No, this is a sum. This is a term in the Hamiltonian, sum of terms. Right? The Hamiltonian is a sum of local terms. The Hamiltonian is a sum of local terms. In the continuum, it's an integral of a density, of the energy density. And on the lattice, it's a sum of local terms. Okay, so now I'm going to answer all these questions. Let's modify the model. So we're going to discuss this model with g equals 0 from this moment on. And we are going to modify it. And the first thing I'll do is what this woman asked. What's your name?
Shreya,
Shia. Where are you from?
UC Irvine.
Irvine. Good. So we'll make the Irvine modification. We'll change G. So we would like at one site, big J, G not to be 1, but e to the minus I eta W. The name is not obvious. So I just changed Gauss law at one point. What does it mean to change Gauss law? You know that already. Gauss knew that. If Gauss law is not 0, but there's something on the right-hand side, it means that there's charge density there. So that looks like charge density at that point. And the gauge symmetry that we had now has charges in it. Now, somebody could say, I don't like that, because I would like to keep the Hilbert space as it was before. So I'll just do a field redefinition and get rid of it. In fact, if I look at the expression for G, only on one side, I have a P, so I'm going to redefine P, shifting it by this eta. So the new model I have still has J equals 1 for all J, but the Hamiltonian is sum over J not equal to J, whatever we had there, plus, what did I call it? U0 over 2 Pj plus eta W over 2 pi square. So we change one term in the Hamiltonian. So instead of changing Gauss law, a big J, yeah, thank you. Big J. And everything else is kept the same. So I just take the term with, so here I have to add a plus sum over all J of the other term square. I'm not writing it. So I take one term in the Hamiltonian, and I shifted P to be P plus eta. If there's only one site in the problem, it's only one this P. This is exactly the example with theta parameter we discussed yesterday. This quantum mechanics is exactly the quantum mechanics of that. Now, as it stands, eta is real number, arbitrary real number. But let me call that h of eta, eta w. There's a unitary transformation I can do if I conjugate the Hamiltonian by phi j. So this Hamiltonian at eta and at eta plus 2 pi are not the same, but they are unitarily equivalent. There's a unitary transformation that shifts eta by 2 pi. So eta is circle valued. Also, I picked a site to insert this guy. Sorry?
Capital J.
J, yeah, capital J. Thank you. Both of you get points. So I picked a point, capital J, special point on the lattice, and I changed the Hamiltonian just there. Now, you say, no, I want to change the Hamiltonian elsewhere by the same amount. Are we discussing the same physics or not? So I put the change in the Hamiltonian at one side, and somebody else put the change in the Hamiltonian at a different point. So I just write the formula, and you can see that all these, no matter where I put this defect, all these Hamiltonians are unitarily equivalent to each other. So there's a unitary transformation that moves this thing. So this thing is called a defect. There's a unitary transformation that H, where I put it at the point J with eta W, is e to the I, so I'm not even going to write it explicitly, UW H at J plus 1, UW inverse. And UW is e to the I, eta W, this is what we call QW J, J plus 1. So this change in the Hamiltonian can be at different points, and they are all unitarily equivalent to each other. That's what people call a defect. In fact, that's what's called a topological defect. What's a topological defect? First of all, why do we call it a defect? Take the same system, the same Hilbert space, the same Gauss law, everything is the same. We picked one site on the lattice, and we changed the Hamiltonian at that point for all times. That's what we call a defect. Nothing happened elsewhere, but at that point, we changed the Hamiltonian. But I have a unitary transformation that allows me to move it to another site. In that sense, it doesn't matter where I put it. So I can put it in any point I want, and the results will be unitarily equivalent to each other. Now I'll do very briefly, so far I discussed everything for the winding. Actually, before I do that, I want to say one more thing. What happens to the momentum, to the winding charge? When I did that, nothing happened. But the momentum charge was the sum of Pj. The sum of Pj is now shifted by this integer, by this real number. So Q momentum of eta W is what it was when it was 0, plus eta W over 2 pi. So this defect does not affect the winding charge, but it makes the momentum charge fractional. So this defect, which is really a defect of the winding symmetry, makes the momentum symmetry fractional. That's really a hallmark of anomaly. We start getting fractional charges even though the symmetry is U1. We get fractional charges. And you can put the link, this thing at the last site, and then say that this is really not a defect, but twisted boundary conditions. So somebody asked me before about twisted boundary conditions. I can also, so I first described this as a modification of Gauss law. Then I said, no, we didn't modify the Gauss law, but we changed the Hamiltonian. And this way, I'm not going to do it in detail, we can also describe it as twisted boundary conditions. So all these things are synonymous. And we can also turn on background gauge field for winding and derive the same result. I haven't done it, but it's really elementary to do it. So you could ask, why did I do it for the winding and not for the momentum? After all, they are all on equal footing. So let me do it for the winding in a quick way. So forget about what we did there. We go back to the original Hamiltonian. And the original Hamiltonian had sum of pj square. I'm not going to write the whole thing. And instead of changing one of the p's, now I'm going to change one of the other terms. So I have here phi, there's phi plus n, all that square. And here I would just write j not equal to big J. And then I'm adding the last term, 1 over 2 pi, phi j plus 1 minus phi j plus same j. I pick one link, 2 pi n j plus 1. So originally we had the square of that, and now I'm writing here eta momentum square. So I changed one term in the Hamiltonian. And you can repeat the same discussion we had before. We added a real number, but we can use a unitary transformation to show that it's actually circle valued. Shifting it by 2 pi can be implemented by a unitary transformation. Also, we put this on the link connecting j and j plus 1. Using a unitary transformation, I can move it to another link. So this is also a topological defect. And here it's even clearer that if we do it for the last link, this is the same as twisted boundary conditions for the phi. So by now I've addressed, somebody asked me about twisted boundary conditions. I think you did. So I addressed that. You asked me about changing Gauss law. I addressed that. And in this form, it also looks like a background gauge field for the momentum. And you can also check what happens to the winding charge of eta momentum, L0, plus, I think I have plus in my conventions, plus eta momentum over 2 pi. So what we see is that we have two symmetries, U1 momentum and U1 winding. Every one of them has a defect, can have several defects, and the momentum defect carries winding charge, fractional winding charge, and the winding defect carries a fractional momentum charge. Now let's make it a little bit more interesting. Imagine we have different kinds of defects at different positions. Where is the colored chalk? Okay. So these are momentum guys, and these are some winding defects. And we showed that we can take this system. We know what it means. This means that take some of the sites and change the Hamiltonian, and take some of the links and change the Hamiltonian. We have a finite number of these with some etas. Now I can use the unitary transformations and move them around. I perform a unitary transformation. I can also move this guy around. Okay. So unitary transformations, these guys, as long as these guys don't talk to each other, I can perform a unitary transformation on these, unitary transformation on these, and the Hamiltonian with these defects is exactly the same, or unitarily equivalent, to a Hamiltonian with these defects. However, so it looks like the defects are completely topological. I'm allowed to move them around. Nothing special happens, except that I was careful here not to let the lines cross. So when the momentum defect crosses the winding defect, we get something non-trivial. And to really drive the lesson, I'm going to write a formula. I want to move both of them to the right. So I first move the momentum, and then I move the winding. This way they don't cross. Or I could say I want to do it in the opposite order. I first move this guy, and later I move this guy. So we started and ending, we started at the same point, we ended at the same point, but along the way, we moved them in different order. What does it mean? Every one of these things is a well-defined unitary transformation on the Hilbert space. Right? Every motion of every defect is a unitary transformation. And I wrote explicitly what the unitary transformation is. I wrote it for the winding here. And the one with the momentum, it's the same thing, but with instead of W, I just write M. So what's the difference between these two? In one case, we had U momentum, U winding, and in the other, we had U winding, U momentum. One of them had in the exponent the charge density of the momentum. The other has in the exponent the charge density of the winding. But they don't commute. These guys don't commute. So if these pictures if I have this K that one of them cancels the other, I have a phase between them. This thing is not the same as that. It's e to the I, eta momentum, eta winding over 2 pi. So the fact that the charge densities don't commute, this Schwinger term, tells us that these defects are not completely topological. We thought they're completely topological because we can move them around by unitary transformations. But the unitary transformations of one kind does not commute with the unitary transformation of the other kind. Yes?
I'm guessing a little confused. Why did you write the order differently in the right side picture? It seems like they both start with like purple on the left, orange on the right.
Yes.
Purple on the left.
Yes. Yes.
What's the difference ordering below the pictures you refer to them?
Because first, here, what do? I start with this, the purple to the left, as you said, and then, let me do it with colors. I first conjugated by this one, U1, and then I conjugated by the purple one. And here, I first conjugated by the purple one, and then conjugated by, what color is this? Pink, whatever. Orange, I can't tell. By the other one. So the unitary transformations act. Now, this is time. This is time evolution. So the system evolves, and then at some point I decided to move the winding guy to the right. At a later time, I moved the momentum guy to the right. Here, I did it in the opposite order. So here I act conjugated by this operator. Here I conjugated by this operator. But this and that, they are not exactly the same, up to some sign that I will not get straight here, eta m, eta w over 2 pi. Because what do we have in the two exponents? One of them has, I wrote it here, one of them has eta w times qw. The other has the same thing with eta m qm. So when you move them in different orders, the charge densities do not commute. This is the Schwinger term. And since the charge densities do not commute, the defects do not commute. If I move them both of them to the right, but in different orders, I get different answers that differ by phase.
Is this like the analog of mutual locality in higher dimension?
This analog of what?
Mutual locality. So like,
There is an analog of that in higher dimensions, but I think the closest to that is braiding in higher dimensions. And then indeed, when two defects wind around each other, if there is a phase, the phase signals an anomaly. But the anomaly there is in a one-form symmetry, and here it's much more elementary. See, I did not use any category theory or, high form symmetries. I just had unitary operators acting on the Hilbert space of a finite number of degrees of freedom. Right? This is much more elementary. And notice that this anomaly is more subtle than the anomaly we had in quantum mechanics. In the anomaly in quantum mechanics, the Hilbert space was in a projective representation. Here, the Hilbert space is not in a projective representation. What is in projective representation is trying to move these defects around. So first, the Hilbert space without defects is not in a projective representation. The Hilbert space with a defect is in a projective representation. As I said, these guys carry fractional charges. Should add parenthetically to be completely correct, some of these fractional charges can be redefined away, but there's still a phase that I cannot get rid of. So the way the anomaly manifests itself here is not that the Hilbert space is in the projective representation, but instead, the Hilbert space with defects is in a projective representation. So I need to add the defects. Let me say it more abstractly, and then I'll go to questions. We said that an anomaly arises when we try to couple the system to background gauge fields, and then the system is not completely gauge invariant. So in the quantum mechanical examples, the only gauge field at our disposal was the gauge field along the time direction, associated with operators, symmetry operators acting on the Hilbert space, and therefore the anomaly was the fact that the symmetry acts projectively. Now we can do more interesting things and introduce gauge fields also in the space directions. And these defects are the same as a gauge field in the space direction. So if we put background gauge field only in the time directions, we don't see anything funny. But we can do something more subtle, introduce gauge fields in the space directions, and these etas are really the holonomies of that gauge field. We introduce gauge fields in the space direction, and we look at the representation, or we act with operators. This is gauge field in the time direction. And together we find that depending on how we set it up, we get different answers, and this can be translated into failure of gauge invariance, which if I have time, I will do. Questions? Yeah?
Say it's like braiding. So in case of braiding, there's this equivalence of right and master. So does that similar?
Okay, I really think I made a mistake that I said it's similar to braiding, because it's similar, but I think it's misleading to think that it's, in the case of braiding, the two lines do not touch each other. Whereas here, they really cross each other. There is something analogous, if you really want, and it's the West-Zumino consistency conditions. But that really goes beyond whatever I said. Yes, there is something analogous. Question?
Yeah, I think related to that, I was thinking that this looks a lot like the setup for like anions and toric code or something like that. But
yeah, there are things which are infinitely more complicated that this is similar to. But this is putting the cart in front of the horse. Take a Hilbert space with 6 sites, with this Hamiltonian, it's completely diagonalized in one-dimensional lattice. I don't need a 2-dimensional lattice. No toric codes, no anions. It's much more elementary. There are many other things that this is similar to. And all these things are associated with some anomaly for something. And there are many other things that are associated with anomalies, and I'm sure you will hear about them later in this school. This is a very elementary example. And the fact that it reminds you of the fancier one shows that this is a good example, because you can see all the subtleties without going to toric code, and that's the same as a modular tensor category, etc. It's not that I don't like the toric code or the modular tensor category. I love them. But this is much more elementary. These are just unitary operators acting on a one-dimensional lattice. Question? Yeah?
Why is there a difference when you introduce a gauge field in time direction versus visual direction?
There isn't. In quantum mechanics, there's only one option, so I can't introduce the other. Here, I really need to do both. If I do only one, I don't see the effect. So what did I do here? First of all, I don't have complete Lorentz invariance because I'm on the lattice. These etas are gauge fields in the space direction. And applying the charge is the same as a gauge field in the time direction. So the fact that the charge was fractional, so all these things come, all these fractions here and the phase here really came from this. And the various charges can be redefined and not have a problem. This phase is unambiguous. It's independent of how you define things. This phase is always there. And it comes from telling us that the defects are not completely topological. Since you asked about gauge field, let me give you another interpretation of that. If we think of what appears here on the blackboard as space-time, and you can think of these defects as we're having a gauge field here, and the defect is a place where what does having a gauge field mean? It means that we cover space-time with patches, and between two patches, we have a transition function. Are these words familiar? Yeah, how many people heard about, thinking about? Okay, great. So what does it mean to turn on gauge fields? For flat gauge fields, it's just the transition functions. For non-flat gauge fields, we need to specify more, but let's limit ourselves to flat gauge fields. So we cover space-time with patches, and between patches, we have a transition function. If the system is gauge invariant, we can draw the patches and the transition functions, we can move them around, it doesn't matter. So think of this thing as being the transition function. This is the transition. So we have two U1s, U1 momentum and U1 winding. This is the transition function for one of them, is here, it's eta momentum, and this is eta winding for the other. Here, we have the same thing, but we drew the patches and the transition functions differently. What is it known when you study fiber bundles? That you change where you move, where you put the transition functions. You change the patches and the transition functions. This has a name. Sorry? Closely related. When you write the bundle in terms of picking patches and drawing the lines between them and have transition functions, it says that you trivialize the bundle. The bundle is trivial except that you have to worry about these transition functions. And what I've done here is a change of trivialization, which is indeed the same as performing a gauge transformation, as you said. And what do we see? We see that the answer changes by a phase. So I changed the trivialization of the bundle, and the result changed by a phase. That means that we lost this gauge invariance. Wasn't too bad. It's only an overall phase. So if I compare the partition function here and the partition function here, they differ by a phase, but it's not exactly the same. That's, again, the sign of an anomaly. Yes?
In a space-time perspective, is this equivalent to unlinking the two defects, or no?
I don't know what linking means, because you don't have linking in 1+1 dimensions. You have a 2+1 dimensional picture in mind.
Yeah,
yeah. It is similar to changing a, yeah. But there, as I said, there the symmetry is one-form symmetry, and it's more, this is more elementary. And you can also see where it happened. It happened at this point. There's a point where all the action was, and it happened because two operators don't commute. That's why it happened. Right? So you see, when you have the linking, it's more subtle, because nothing touches anything. So you can't say where it happened. Here it happened because of these 2 points, that these operators don't commute. There's another symmetry in this problem which we haven't used yet, and that's translation symmetry. So we have a lattice with L sides. So we have translation T to the L is 1. And the way T acts on an operator at the side J, it moves it to the side J plus 1. That's a defining property. So that means that we have a ZL translation symmetry. We can also add parity, but let's not do that. Maybe also time reversal. So that's before we introduce the defects. What happens when we introduce the defects? Why do we have the symmetry? Because if I look at this Hamiltonian, I've already killed this guy. If I look at this Hamiltonian, wherever I see J, I'm going to write J plus 1, I'm going to find the same Hamiltonian. But that's not true when I have a defect. So with a defect, we lost the symmetry. Why? Because when I move j to j plus 1, most of the terms move correctly, except one term. There was a term with a defect, and it moves to a term without a defect, and a term without a defect now has a defect. However, I said before that these two problems are not exactly the same, but they are unitarily equivalent. There is a unitary transformation that brings the defect back. So T is no longer a symmetry, but T times this U that I discussed, or was here? The operator that shifts by one side. Where was it? Here. The operator that shifts by one side, U of eta, that is a symmetry. So what do? I shift wherever I see little j, I write little j plus 1. And then I apply the unitary transformation. I did it in the opposite order. First do this, and then I apply the unitary transformation to bring it back to where it was. So this guy is better than the original T because it does commute with the Hamiltonian. However, it doesn't satisfy this equation. And you can check if I have only one kind of defect, T to the L is not 1, T eta. Eta to the L is not 1, but it's e to the I eta times the charge. Have we seen it before? Twisted boundary conditions. That's the hallmark of twisted boundary conditions. So we see here from another perspective why, when we add the defect, this is the same as not having the defect, but putting twisted boundary conditions. So the symmetry algebra is no longer T to the L equals 1, is no longer ZL, but the symmetry algebra is different. We have a U1 here with Q, and we have some translation, but they mix together because of the twisted boundary conditions. So since we have a new group, we have an opportunity to see new funny phases. And this was my plan for today, but this will have to wait. I'll show you that all these relations have funny phases. And these equations like that have phases which reflect, again, the same anomaly. So I guess I have to stop now, right? You didn't notice that the time passes.
No, I noticed. I said I'd give you a couple extra minutes.
A couple of extra minutes. OK, so I can do that. Great. So I can actually finish that. So as I said before, if we have only one kind of defect, only momentum defects, it doesn't matter how many. We can fuse them all together, and there's only the total twist, the total eta M, or the total eta W. There is no problem. But this thing is more interesting because so in terms of anomalies, it means that U1 momentum on its own does not have anomalies. U1 winding on its own does not have anomalies, but we have mixed anomaly between them. So only when both of them are present do we see that there is anything funny. So let's introduce both of them. So I'm going to introduce both of them and do the same exercise. So T is no longer conserved because I have all these defects, but instead I can multiply it by all these U's. Let me put it on the right. So I can put here all the U's, and this has both eta momentum and winding. I don't remember whether I put it as a superscript or a subscript. So this operator involves the original translation operator accompanied by a unitary transformation. So what does it mean? I act with T, it moves J to J plus 1, and then whatever defects I had, I move them by one side to the right. If I have only one kind of defect, no problem. But if I have both of them, and I move them to the right, this subtlety could be important. In which order do we move them to the right? And that's particularly important if we try to compute t to the L. So we do that L times. So call that t of eta. T of eta raised to the Lth power. So naively, where are my two colors? The purple and the whatever it is, pink. So naively, it should be not 1, but e to the I eta m qm times e to the I eta w qw. This is what twisted boundary conditions would tell me. So that if I take t to the L, it means I went all the way around space. The boundary conditions are twisted by a symmetry transformation. So that's what the twist does. However, if you do it carefully, and it's a little bit of an algebra, this phase comes in. And this equation is actually not true. And I'll use a different color, blue. Over 2 pi. In this phase, one cannot get rid of. So what we see is that without defects, there's nothing funny. We have ZL translation. We have U1 momentum, U1 winding. The charge densities or the currents don't commute. And this fact, the Schwinger term, propagates into other things. It tells us that the defects carry fractional charge. The momentum defect carries fractional winding charge. The winding defect carries fractional momentum charge. And one might want to redefine them away. One could redefine them away and say, let's set them to 0. These changes are only sin numbers. But this blue phase, one cannot get rid of. So you can change these guys, shifting them by a sin number, shift this by a sin number. That will have the effect of flipping the sign here. So you can move phases around, as I discussed before. And that's common with anomalies. That's why it's involved cohomology. You find some phases, then you can try and redefine things, get rid of the phases you don't want. But some phases remain. So what we see here is that U1 momentum and U1 winding and the translation satisfy this equation. I think I'm good. So toward the end, I kind of rushed because I wanted to reach a point and discuss a different topic tomorrow. Not tomorrow, the day after. But if there are any questions, feel free to, I'm around, including tomorrow when I'm not lecturing. Try and grab me and ask questions. I'll be happy to answer, especially where I rush toward the end.
Just to clarify what you said versus the equation, should TH not the presence of the defect?
Does this answer your question?
I think so. Yeah, I'm just comparing this story
Yeah.
to TH.
So now you have to put, yeah. So if you look at all the operators, H depends on eta because we change H at one point or at several points. T depends on eta because we multiplied it by some unitary transformation. And the reason we multiplied it by unitary transformation was such that this equation would be true. So we changed the Hamiltonian. We broke the original symmetry. But there's a cousin of the original symmetry, which is a symmetry.
And the top commutator with defect.
Thank you.